Welcome back to the SysML V2 Deep Dive series. In the previous lesson, we used connection and interface usages to make the topology between a charger and vehicle explicit. But a connection tells us where the system is connected. It does not yet define what moves through that connection. In this lesson, we will use item definitions to model the stuff that can exist, be stored, and flow through a system, such as fuel, data, or electricity. In SysML v1, engineers modeled the things that flow through a system by typing a flow property or an item flow with a standard block, value type, or signal. While this successfully gave the payload structural properties, allowing you to specify the density or octane level of fuel rather than just an anonymous flow rate, it meant using the exact same generic block construct for a passive payload as you used for an active system component. SysML v2 introduces greater semantic precision by providing the item def. According to the SysML v2 abstract syntax, an item definition is a specific kind of occurrence definition used for things that exist in space and time and can be acted upon, but which do not necessarily perform actions themselves. This gives us a dedicated construct to separate the active components of our system, modeled as parts, from the passive payloads moving through them, modeled as items. Instead of using a generic block, we can model our fuel explicitly as an item def with its own properties and rules, and then route it across our defined interfaces. That is useful for physical matter, but the idea is broader. A payment credential, a sensor reading, a software packet, and electrical energy can all be modeled as items. The definition usage pattern applies here just as it does for parts and ports. An item def defines a reusable type of thing. Because it is a definition, it can natively own its own attributes, internal structures, and constraints. An item is a usage of that definition. Inside a port, a directed item feature declares the capacity to exchange that item. Inside a part, an item usage can represent contents that the part stores. This distinction is important. A port does not contain fuel merely because it declares an out item. It defines the system's ability to send that type of fuel. Conversely, a tank that owns an item usage represents fuel that is physically present and retained within that structural boundary. Here is a package that defines physical fuel and digital payment data, then uses the fuel definition in a nozzle port. Feel free to follow along with a free account on SysModeler.ai. Let's walk through it. The package imports 4 libraries. ISQ provides quantity types such as mass density value and time. SI provides the specific measurement scales like kilograms and meters. Time provides chronological concepts. And scalar values provides standard scalar types such as real and string. We first define fuel. Fuel is not just a label attached to a connector. It is a typed model element with an octane level and a density. The density is explicitly a mass density value, rather than an unqualified number, so the model can retain the physical quantity involved. The constraint adds a rule to that definition. The unit in 700 kilograms per meter cube gives the expression a dimension that can be checked against density. That makes the rule more than a comment. A tool can reason about whether the quantity and unit are compatible. Next, we define an information item. Items are not limited to physical matter. Payment data has information-specific properties, while fuel has physical properties. Also notice that the timestamp is typed as datetime, a specific value type provided by the time package. Both physical fuel and digital data are things the system can exchange or retain, so both perfectly fit the item def construct. Finally, the port declares an outgoing item feature. Super unleaded is an item usage typed by fuel. The out direction says that a usage of nozzle port can send this fuel outward through the port. It does not mean the nozzle is actively dispensing fuel at every moment. It structurally defines the port's boundaries. The same fuel definition can also represent storage. For example, a fuel tank part could own an item usage typed by fuel to represent the mass it actually contains. The underlying definition stays the same. The structural context, whether it is an out item in a port or an item nested inside a part, tells the modeling engine whether the payload is being exchanged or retained. Because the payload has a type and properties, tool can do more than display a label on a connection. They can check that an item feature is typed by an available definition, evaluate constraints against property values, and check dimensional consistency in expressions involving quantities and units. They can also follow a specific item type through ports, connections, and storage locations when analyzing flow or mass balance. There is also a useful modeling convention to keep in mind. In the SysML v2 ontology, a part is a specialized kind of item. In day-to-day system models, we normally use part for a system element that performs actions and item for an operand that is moved, stored, or processed. Using those roles consistently makes the model easier for people and tools to interpret. Before we wrap up, here is the shift in compact form. In SysML v1, exchanged payload is modeled using an item flow that was typed by a generic block, value type, or signal. In SysML v2, it is defined explicitly with an item def, isolating passive payloads from active structural blocks. In SysML v1, port flow declaration was done through a flow property on a port or interface construct. In SysML v2, it is a directed item feature inside a port def. In SysML v1, value type often used to stand in for the payload itself. SysML v2 uses attribute def or a cur-ml data type for values and item def for the exchanged thing. In SysML v1, you had to create a separate item flow relationship. And in SysML v2, you use a flow usage when modeling the flow itself. The key idea is that SysML v2 separates the thing being exchanged from the values that describe it. Fuel is the item. Its density and octane level are attributes. That separation lets the model preserve both the payload's identity and the engineering data needed to reason about it. We now have ports for interaction, explicit connections for topology, and item definitions for the physical and digital things that move through the system. In the next lesson, we will look at specialization and redefinition, two related mechanisms for building reusable model structures while controlling exactly what a more specific model inherits or changes. See you there.